Let's review a couple definitions involving continuity. So we have continuity at a point. Let f be a function and c a real number, then f is continuous at c if the limit as x approaches c of the function equals f of c. And then we had definition of continuity on an interval. Let f be a function and suppose that f is continuous at every number in an open interval ab. Then we say that f is continuous on the open interval ab. So now we're going to use these definitions to figure out what kinds of functions are continuous. So, what kinds of functions are continuous? Well, all of the following types of functions are continuous everywhere in their domain. So, for example, polynomial functions. We know polynomial functions have a domain of all real numbers, so polynomial functions are continuous for all real numbers. Trigonometric functions. Well, we know sine and cosine are continuous. If we just look at the regular sine of x or cosine of x, those are continuous for all real numbers. And then things like tangent and cotangent, secant and cosecant, those are continuous everywhere in their domain. So the places, of course, that are not in the domain, it's not continuous there, but everywhere else, it is continuous. Same goes for exponential functions. That would be like your e to the x or 2 to the x or 3 to the x. Those are continuous everywhere. And logarithmic functions are continuous everywhere in their domain. And root functions, like the square root of x, those are continuous everywhere in their domain. And rational functions are continuous everywhere in their domain. And again, the in their domain part is the key part here. We know that rational functions sometimes could have vertical asymptotes, and they would not be continuous at places like that. But they are continuous everywhere in their domain. So what about combinations of functions? So let f and g be continuous at a. Then we can say that f plus g is continuous at a, f minus g is continuous at a, c times f is continuous at a, where c is a constant, and f times g is continuous at a. And finally, f divided by g is continuous at a only if g of a is not equal to 0. So think about rational functions here. We know that rational functions are continuous everywhere in their domain. Well, rational functions we can think of as just one polynomial divided by another. And as long as the denominator doesn't equal 0, then we have something that's continuous. So let f and g be continuous at a, and we'll look at what happens when f plus g is continuous at a. So this was the first bullet point from the last slide. So let's figure out why this is true. So here's the definition for what it means to be continuous at a point. This was just the same definition I had from the very first slide. And this is the limit as x approaches a now of f plus g. We're looking at the sum of two functions. And if we're going to show that f plus g is continuous at a, then we want to show that the limit as x approaches a of f plus g at x equals f plus g at a. Well, the first thing I can do is I can break this up. And if you remember, this is just the limit law that says that the limit of the sum of functions is equal to the sum of the limits. So this is one of the limit laws that we had from one of the earlier slides, or one of the earlier videos. Then the next thing we can do is we can apply the definition of what it means to be continuous. So we see that f and g are continuous at a. Well, if they're continuous by this definition up here, we know that the limit as x approaches a of f of x is f of a, and the limit as x approaches a of g of x is g of a. So this right here, that's just the definition of what it means to be continuous. So definition of continuity. And that's what we have up in the corner of the slide here. And then finally, the last step, we can just say that this is the same thing as f plus g at a. And this is just what it means to say that you're adding functions. This is a definition of function addition. So this was a very, very simple proof. I mean, it wasn't even really a formal proof, but you get the idea, and you can see how all of the other bullet points from the previous slide could be shown to be true in a very similar way. So what about composition of functions? So first, I'm going to do something that's going to lead us towards an idea about composition of functions. So first I'm going to look at limit as x approaches a of g of x, suppose that's b, and suppose that f is continuous at b. Then what we can do is we can actually pull the limit inside of the function. So the limit as x approaches a of f of g of x equals f of the limit as x approaches a of g of x, and that equals f of b. And this also works if you let x approach a from the right or from the left, or even if you replace all of the x approaches a's with x approaches infinity or x approaches negative infinity. So let's look at an example. Suppose I have f of x equaling, and we'll say x squared. And let's suppose I have g of x equaling, how about sine of x? Okay, and we'll let, let's see, how about if we let a be pi over 2? So in this example here. Okay, so we're going to look at the limit as x approaches pi over 2 of f of g of x. Well, what is f of g of x? F of g of x is sine of x squared. So I'm saying that that's the same thing as if we imagine bringing the limit inside the square here. So that would be the same thing as saying the limit as x approaches pi over 2 of sine of x whole thing squared. Okay, well, what's that? We know that the limit as x approaches pi over 2 of sine of x is 1. So this is like 1 squared, which is 1. And we said that this was f of b, where the limit as x approaches a of g of x was what we called b. Well, that's this thing right here that's inside here. That was 1. And so, yeah, this is the same thing as f of 1. 1 squared is 1. So same thing, this does indeed work. Okay, so I have this thing here that we just saw an example of, and then I also have the definition of continuity at a point. So now let's look at composition of functions. Suppose g is continuous at a and f is continuous at g of a, then f composed with g is continuous at a. So to show this, I want to show that the limit as x approaches a of f composed of g of x equals f composed of g at a. That's what it means to be continuous by the definition. Well, I can rewrite the function composition. F composed of g of x is just f of g of x. And then I can use the first statement above and pull the limit inside. So that's equal to f of the limit as x approaches a of g of x. But I know that g is continuous at a. So the limit as x approaches a of g of x is just g of a. So this is f of g of a. But f of g of a, rewriting it in terms of function composition, is just f composed of g at a. And so that does indeed show that this is true. So here's what we just showed, and let's look at an example. How about if f of x is the absolute value of x, g of x is x squared minus 4, and then f of g of x would be the absolute value of x squared minus 4. Now, according to what we just saw here, if we're looking at continuity, we know that, for instance, g is a polynomial function, so it's actually continuous everywhere. And then we also have absolute value, and we happen to know that absolute value happens to be continuous everywhere also. So we would expect that f of g of x here should also be continuous everywhere. And in fact, if we look at a graph of the absolute value of x squared minus 4, we do indeed see that it is continuous everywhere.